This is our group's project on proportionally controlled heating of water using pulse width modulation. I'm Abe.
I'm Hollis.
And I'm Katie. Okay, so our problem statement, we wanted to create a system that could control heating water to a specific temperature, and in our case, we did 100 degrees C, so boiling temperature for water. We also didn't want to go over 100 degrees, we wanted to approach 100 degrees and steady off, and we wanted to minimize our steady state air. Using LabVIEW, we wanted to create this type of program because it can be applied to a variety of assistive technology applications.
Our project required controller effort modification, and we decided to do this using proportional control, which is a part of PID control for closed systems. So we modified the controller effort by scaling the air input by a constant, which we call K sub P. And we calculated K sub P using a linear curve that depended on our desired temperature, which in our case was 100 degrees C. And you can see the relationship between the air, the constant, and the controller effort in the equation below.
We chose pulse width modulation as our method of reducing the total energy received by the hot plate. It works by cutting off the power to the hot plate for a percentage of each alternating current cycle. And that percentage is called the duty cycle. Duty cycle of 0 implies that the power is completely off for the entire cycle. 0.5 is 50-50, half on, half off, and 1 is always on.
Now we're going to talk about the methods that we used in our setup. So first we had a hot plate that had a beaker of water on top of it, and inside the water was a thermocouple, which we used to measure a signal and read into LabVIEW. And from this signal we filtered it and converted it into an average temperature. We took this average temperature and subtracted it from 100 degrees Celsius to get our air. And if our air is greater than 30%, our duty cycle is 1, meaning our hot plate was fully powered and fully on. So once the water reached a temperature of 70 degrees C, our proportional control effort kicked in, and our duty cycle was decreasing from 70 degrees until we got to 100 degrees. So our duty cycle was decreasing from 1 down to 0.3, which is where our steady state temperature occurred with a duty cycle of 0.3. Value of the duty cycle was output through a DAC module to a relay, which was hooked up to the hot plate, which controlled the amount of power that was going to the hot plate.
Okay, this video shows our experimental setup. So on the floor, you can see the beaker full of water just sitting on a hot plate, and it has a thermocouple in it, which reads voltages into the DAC, which sends them to LabVIEW, which converts them to a temperature. That clicking you hear is the relay, which is powering the hot plate based on the duty cycle that is calculated by LabVIEW. That clicking matches the light on the DAC module. This is all powered by an external power source because LabVIEW is not powerful to do it on its own. You can see here our panels in LabVIEW, the block diagram, and our output terminal, so to speak. And we have here the duty cycle of approximately 0.3, which corresponds to our steady state. And we can see the temperature output here. And that's about it.
This is our LabVIEW block diagram. You can see the data is read in through the DAC Assistant and filtered and scaled to create the arithmetic mean. Then our error is calculated from that. If that error is greater than 30%, then our first logic statement reads true, and a constant 1 is output for the duty cycle. Otherwise, our proportional control takes into effect. Our second logic statement checks if our temperature is greater than 95 degrees, and if so, outputs a duty cycle that should keep the temperature constant, otherwise it continues to use our proportional control. All of that final duty cycle is output into another block diagram, which will be shown on the next slide.
So what you can see here is the expanded block diagram from the previous slide, And this was modified from a pre-existing block diagram in LabVIEW. And basically what it does is it takes the value of the duty cycle and outputs it to our relay.
So in conclusion, pulse width modulation is more energy efficient in keeping a device running at a specific power level than traditional methods. Our system was able to hold a beaker of water at 80 degrees Celsius indefinitely with a duty cycle of approximately 0.3. This pulse width modulation system can be used in many different applications that require controlled heating. For example, preheating an oven, or in experiments that require controlled heating of a substance. In addition, we hope that future students in the mechanical systems laboratory are able to use our template for pulse width modulation control in their own applications.
To thank Dr. Doty and his excellent lab assistant Nathan for helping us make this project possible. And thank you for listening to our presentation on pulse width modulation and proportional control for heating water.